To study motion inside a galaxy, the problem is that we do not actually see any movement. A normal galaxy looks unchanging from year to year and from century to century. What we can measure is the Doppler shift in the line of sight direction, the radial velocity, relative to the average galaxy as a whole. To convert this into speed in the plane of the disk, the rotation speed, we presume that the disk is actually circular, and that tells us the angle of inclination. You'll be doing this for yourself in a later video sequence. The radial velocity varies across the galaxy because of the varying orbital speed. This is shown in this colourful depiction of 21 centimetre line observations. Material moving towards us relative to the average is coloured blue, and as we look across the galaxy, material moving away from us is coloured red. To study motion inside a galaxy, the problem is that we do not actually see any movement. A normal galaxy looks unchanging from year to year and from century to century. What we can measure is the Doppler shift in the line of sight direction, the radial velocity, relative to the average galaxy as a whole. To convert this into speed in the plane of the disk, the rotation speed, we presume that the disk is actually circular, and that tells us the angle of inclination. You'll be doing this for yourself in a later video sequence. The radial velocity varies across the galaxy because of the varying orbital speed. This is shown in this colourful depiction of 21 centimetre line observations. Material moving towards us relative to the average is coloured blue, and as we look across the galaxy, material moving away from us is coloured red. The change from one side to the other indicates that the galaxy is rotating. Here's another galaxy. Again, the colours show that it's rotating, and here's a third example. All spiral galaxies that have been measured show essentially the same pattern of rotation, the same rotation curve. To examine the motion in the plane of the disk, we have generated some computer models. This is a disk. We see it moving here like a gramophone record. The pink spot is about the distance of the Sun from the centre of our visible galaxy, a scale to fit on the screen. It gives us something to identify. If there are spiral arms in this disk, rotating as a solid body like a gramophone record, the pattern of these arms is maintained. However, a real galaxy does not rotate in this solid body manner. Instead, it's rotating differentially. We look at it first without the spiral structure. Material further out from the centre takes longer to go round. Now look at a structure within the differentially rotating material. The outer parts trail behind more and more. In a short time it winds up completely and the structure disappears. This presents a severe problem. Real galaxies have spiral arms that are not wound up. So the answer must be that the spiral structure is a permanent pattern that does not share in the differential rotation. The pattern goes round at a much slower, uniform rate. The material rotates differentially, passing into the pattern and out again. In the density wave theory, the pattern is a concentration of the material. When it enters a spiral arm, it slows up and takes longer to get through. Inside the spiral arm, the density is greater. This is a simple model to show the essential motion. In the theory, the gravitational field produced by the pattern keeps the pattern going, and so it goes on.
The radio signals from space are extremely weak. So that's why, for research purposes, we use giant reflectors like the 76-meter telescope at Jodrell Bank behind me. We can't really dedicate telescopes of this size for student use, but what we can do is look at stronger sources, like the galaxy in M33, rather close by to us, and for that study of strong sources, we can use smaller telescopes, like the 6.5-meter telescope behind me. We've outfitted this telescope with professional-level equipment, and it's perfectly capable of studying the galaxy M33 and indeed of weighing the galaxy, and this is the project for you. The weak signals from the galaxy hit the dish surface and are picked up by the feed horn in the center. They're then sent round to the back of the dish where they're intercepted by a very sensitive transistor amplifier, and the amplified signals are sent into the cabin behind me where they're further processed, and that's where your work starts.
Okay, Emma, what have you got there then?
Okay, the receiver splits the signal into 64 bands across here. Here's one of them. Each band is 62.5 kilohertz wide. This spectrum we're looking at here is of our galaxy, the Milky Way, and it's split into two components. This frequency here corresponds to the frequency that hydrogen emits at when it's not moving. This is hydrogen's rest frequency. But because we're looking at this longitude here, we're looking at hydrogen that's towards the centre of our galaxy, so we're getting hydrogen that's moving faster than us and moving slower than us, so we're seeing a split profile. If we look at another longitude, that's 90 degrees, we see the profile much fatter and it's become more one component. And then we also have, this is at longitude 200 degrees, and we're only seeing hydrogen here that's further away from the centre of the galaxy than we are, so we're only getting one component of the emission.
I'll show you the plots again and give you an outline of the comments in the notes, which you should work through after you've viewed this sequence. Here's the data taken along the line in green, which is at 40 degrees to the direction to the centre of our galaxy, which is shown dotted. To see what it means, let's first imagine a simple case. Suppose that there were a cloud of hydrogen in the area marked with a square and numbered number 1. It's on the same orbit as us, so the Sun and the square move around together, keeping the same distance between us. There's no relative velocity, so we would receive radiation at the same frequency at which it was emitted, the rest frequency. No Doppler shift. But look what was actually observed, and we see that it is split in two. So there were at least two clouds at different distances, and because of the differential rotation, cloud 2 is going faster than us. That is, the distance from us to cloud 2 is increasing, so we see a redshift. Whereas we're catching up, cloud 3, decreasing distance, blue shifted. The blue line shows the direction of the longitude of 90 degrees, which corresponds to the direction that we're travelling in. So we're closing in on the cloud shown as number 4. And the observations do indeed show a marked blue shift. What about the 200-degree plot? This shows a small shift. This direction is close to the radially outward direction, which would be 180 degrees. In that direction, clouds in circular orbits are running parallel to us, so they would have 0 radial velocity relative to the Sun. It's not surprising, therefore, that the Doppler shifts observed at 200 degrees are small. Look at cloud 5. In TV6, you see data from a complete set of directions, and they combine to show a clear pattern. But even astronomers find it very difficult to turn that pattern into a map. So we're not expecting you to do any difficult calculations on these data. We want you to see the principles involved. The difficulties in making maps arise because we're inside our own galaxy. Turning now from our own galaxy to other galaxies, such as M33, we find it much easier to draw definite conclusions from the data. Let's join Stuart and Emma again.
Should we compare that velocity width with the galaxy that we observed last night?
You mean M33?
Yes.
Well, that's here.
What's that spike there?
Well, I think that must be local hydrogen that we failed to subtract completely, but it's quite useful because it allows us to show where the 0 of hydrogen emission is. But the actual scan across M33 is very nice. All we have to do now is remove this low level of noise, which increases at a regular interval as the frequency increases. So if we judge that, we can measure the width of M33
We only need to count the number of channels.
in frequency. So 1, 2.
It's about 15.
15, 16. I think 16 actually.
Yeah.
Yes. And how wide?
62.5 kilohertz.
That allows us to work out the direct width of M33. So how does that compare with local hydrogen?
Well, this is only about 3 or 4 channels wide.
So why is that
There's
so much
much
narrower?
less of a velocity spread there. The hydrogen is moving more or less at the same velocity in this case.
So the hydrogen line emission from M33 is drawn out into a broad band by the rotation of the entire galaxy. But that whole band is displaced sideways from the rest frequency. Why do you think that is? Read off the displacement in megahertz, either from the plot on the screen or the diagram in the notes, and make sure that you can explain this displacement before going any further. Check your answer by looking at the notes. Now, let's look at the broadband itself. The width of the band in megahertz is a difference in frequency corresponding to the difference in radial velocity between the approaching side of the galaxy and the receding side. First, convert the frequency width to a velocity width. The notes explain how. Now we see the effects of the orbital rotation thanks to the fact that the galaxy is tilted. And notice that the image looks elliptical, but it's a spiral galaxy, so we must assume that it is in reality circular, not elliptical, and that the tilt has turned the circle into an ellipse. If you're not sure of that, take a dinner plate at arm's length and tilt it slowly towards you. In fact, if you do that and look carefully at the shape you see, you may even be able to guess the tilt of M33. But we give you the angle in the notes and the corresponding factor by which you multiply to get the true orbital velocity in the plane of the galaxy. Now, that's already interesting, but we can go further if you're prepared to take 2 things on trust. The first is the distance of M33, found from other work to be about 2.5 million light-years. Now, if we superimpose the angular scale of the photograph, you can estimate the radius of the visible image in seconds of arc. Try that now. There's some judgment involved, but make your best guess. That's what astronomers do too. Multiplying the distance by the angle, using the proper units as explained in the notes, gives the radius. Now comes the second assumption. It relates to the band edges where the frequency shifts are greatest with respect to the centre of the band. Clearly the centre of the band is associated with the centre of M33, but we'll also suppose that the frequency shifts at the edges of the band correspond to material at the edges of the visible image of the galaxy. In other words, to the orbital radius that you've just worked out. Is that a reasonable assumption? Well, there's a lot bound up with that assumption, which we'll go through in the notes. But given that assumption, all you have to do now is to apply Newton's law of gravity in the form given in the notes. And if you manage to do that, you'll have weighed a galaxy.
These are galaxies, almost at the limit of the visible universe. Cosmic architecture on the largest scale. To understand how this architecture came about, its details must first be firmly established by constructing maps to show in what direction the galaxies lie and how far off.
So the aim is to measure the distribution of galaxies on large scales in the universe, and this is done in two stages. Firstly, large glass photographs are taken on a telescope in Australia, the Schmidt telescope, and then those photographs are scanned here by a laser-controlled plate measuring machine. The aim of this first stage is to measure the positions precisely on the sky of galaxies, and also to tell the difference between those galaxies and the stars in our own Milky Way galaxy. Now, to tell the difference between a star and a galaxy, here we've got a very small section of the photographic plate as scanned by this APM machine. And this is just an area that's 4 millimeters on the plate, very small fraction of the data that's on this photographic plate. And here we see a few galaxies and stars. A galaxy image is, of course, rather fuzzy and faint, has a low surface brightness, whereas a star in our own galaxy is very sharp, round, and has a bright core. And it's this essential difference between the images that allows the computer automatically to tell the difference between a star and a galaxy. A catalogue is then made up of all the faint galaxies down to some fixed brightness limit, and this is then taken by the astronomer to a larger telescope in order to measure the spectrum of the light from each of these galaxies to determine its redshift. The redshift is that essential third dimension in the position of a galaxy in space. So it's a two-stage procedure. The first stage is to measure the plates. This gives us the two-dimensional positions of the galaxies on the sky. And then the second stage is to measure the redshift of the galaxy with a larger telescope, and this gives us the valuable third dimension. Now, we shouldn't underestimate the size of the task, and just to illustrate that, I'll show you here the amount of data that comes from these plates when they're scanned by this APM machine. This rack of magnetic tapes represents all of the digital data that is recorded from the plates in the southern hemisphere. You can see it really is a large amount of data. But the ultimate goal is very worthwhile because understanding the spatial distribution of galaxies in the universe is a very important cosmological question. Let's just go and have a look now at some of the scientific results. So each of these areas has been scanned by the APM plate measuring machine, and so the distribution of galaxies in two dimensions has been built up, ready for measuring the distances with the spectrographs on the larger telescopes. Now, for bright galaxies, their numbers on the sky are sufficiently small that one measures them one by one with the large telescopes and slowly builds up a three-dimensional map of the distribution of galaxies in the local universe. And here is one of those such maps, and it represents a sort of wedge diagram where the observer is at the apex of the wedge, and as you go out you're measuring to larger and larger distances with the angle across the wedge itself. And you can see that the distribution of galaxies is highly non-random. There are large clumps, clusters of galaxies on scales of 1 megaparsec or so, superclusters on scales of 10 megaparsecs, 20 megaparsecs, and even bridges and sheets joining these clusters on scales much larger. One of the most surprising results that has come out of the very nearby redshift surveys was the discovery of the Great Wall, a huge chain of galaxies about 100 megaparsecs long, which is one of the largest structures in the local universe. Now, astronomers are very concerned about these kind of structures, how they grew and formed in the early universe, but also whether the universe is really homogeneous on large scales. After all, this is a fundamental question in modern cosmology. In order to check that, we need to go to even larger scales, and survey the universe in larger volumes still. Now here a new instrumental technique makes measuring the redshifts much easier. By going to very large distances, we see many more galaxies, of course, and so their surface density on the sky is very much higher. Then we can use a fiber optic technique, where the light of each faint galaxy is fed by an optical fiber into the spectrograph, enabling us to measure the redshifts of galaxies, not one at a time, but 50 or 100 times simultaneously. This means that, of course, we can measure redshifts much quicker than we would otherwise be able to do. Now, the results that come out of these fiber optic surveys, which are essentially a very deep pencil beam in space, sort of like a borehole into the deep universe, are shown on this diagram here. And here one is looking at the distribution of galaxies in a single one-dimensional line. This is what one would expect if galaxies were distributed uniformly, and you can see the distribution isn't anything like that. It's very, very clustered and spiky. And fortunately, one of these spikes goes right through this Great Wall, and so one is, in a sense, intersecting wall after wall in making these deep pencil beam surveys. This was a very surprising result. Although we knew of the existence of the Great Wall, we didn't know how many such structures there might be in the universe. In fact, it appears that they're very common. Now, it's this complementary picture here between the local surveys, which cover a wide panoramic angle, but perforce have to study the galaxies one by one, and the deep pencil beam surveys here, which show the distribution of galaxies along a single line, that give us our picture of the current distribution of galaxies. In the future, what we would like to do is, of course, to open up the panoramic angle and go deep, and that's where the new telescopes, which will simultaneously have a wide field of view and have this fiber optic gain, will enable us to get the best picture of the distribution of galaxies in the deep universe.
These three-dimensional surveys are obviously the ultimate goal, but they are going to take a long time to complete. Fortunately, a good deal can be learned from two-dimensional surveys, directions without distances.
Although three-dimensional surveys have given us a good visual impression of what structure in the universe looks like, there is in fact much more data in two dimensions. We have surveys of several million galaxies, in fact, whereas only 30,000 galaxies have measured redshifts. So we can get much more accurate results from two-dimensional surveys. The results show that galaxies are clustered out to scales of about 100 megaparsecs. On larger scales, the universe is very nearly homogeneous.
How do astronomers explain this large-scale distribution of galaxies? First, they have to understand how the galaxies themselves form.
Understanding the formation of galaxies is one of the biggest problems in modern cosmology. We believe that the universe started off from a hot, dense initial state. Shortly after the Big Bang, small irregularities were generated by exotic physical processes, and these grew under the action of gravity to make the structure that we see in the universe today. Now, can we deduce, by looking at observations, what the starting conditions in the universe were like? I can illustrate this by looking at computer simulations. Here is a simulation of a slice of the universe. It is 300 megaparsecs by 300 megaparsecs by 30 megaparsecs deep, and shows that galaxies are clustered strongly on large scales. We see filaments, bubbles, and voids. Here is the simulation at an earlier time, when the universe was only 15% of its present age. The structure is less pronounced, and shows how gravity amplifies small irregularities to form galaxies, clusters of galaxies, and superclusters. I've run lots of simulations like this, and it's interesting to ask whether we can tell the differences between different theoretical models. This isn't easy, as illustrated by these two models. On one side, I have a computer simulation which is designed to reproduce what we see in the real universe. On the other side, I have a simulation of the cold dark matter model. The two models are rather similar, and in fact we have to apply rather complicated statistical analyses to distinguish between them. In fact, the results fit in quite well with models with cold dark matter, but to make a precise match with the observations, some extra ingredient is required. So cold dark matter with perhaps a trace of hot dark matter in the form of massive neutrinos provides a good match to the observations. Another possibility is to have a cosmological constant from Einstein's theory of general relativity, and together with cold dark matter, we can make models which work. To distinguish between those models requires more difficult and complicated observations. For example, looking at the motions between galaxies or looking at the anisotropies in the microwave background.
Exciting new intellectual territory is opening up here. Einstein's theory of general relativity and the microwave background radiation. These concepts are so important that much of the next block of this course is devoted to them. By the end of this final block, you will appreciate more fully how the large-scale distribution of the galaxies can be explained.
The important gravitational forces in galaxy formation are thought to be those due to dark matter. To model the formation of galaxies, we don't have to know what the dark matter is, as long as we can put in its gravitational effect. In observations, visible matter acts as a tracer for what the dark matter is doing. But in simulations, the dark matter is programmed in and can be displayed.
Okay, this shows a sphere of primordial material consisting of both gas and dark material that's separated off from the Hubble expansion and is about to collapse in itself to form 3 galaxies. As it collapses down, the initial noise in the system amplifies, and in the final big crunch and re-expansion, we get the nucleation of the central region of the first galaxy, showing in the green. And down at the bottom, a second galactic nucleus forms. And these long linear features then wrap up to form spiral arms, forming a spiral galaxy on the left and a barred spiral on the bottom. Top right, sections of subgalactic material merge to form an elliptical galaxy. So we end up with a spiral, elliptical, and a barred galaxy.
Using this simulation, we can also look at the dark matter on its own. The dark matter forms the bulk of the mass of the galaxy and so governs the whole process. To find out if galaxies are forming today, it's no use just watching a galaxy to see if it changes. It would take far too long, millions of years. So here's a more roundabout way. This is a simulation of the stage galaxies had reached when the universe was 5,000 million years old. It was created by George F. Statio at Oxford University. The biggest galaxies formed first, where the density concentrations were greatest. The big reddish blob contains large numbers of older, redder, low-mass stars. But lots of small galaxies also form at the same time, with bluer, more massive stars which burn out quickly. There are many such blue galaxies in the simulation. But what about the real universe? Well, when we look deep into space at a redshift of z equals 1, which corresponds to the age used for the simulation, we do indeed see such small blue galaxies. So that suggests that the simulation is working well. And incidentally, looking at the current stage of the universe, that is at small redshifts, much less than 1, we do not see small blue galaxies, and this suggests that there are not galaxies forming nowadays. But notice that this is a very indirect way of getting to an answer, and it's not conclusive. Although we don't see galaxies in formation, what we do see quite often are clear signs of galaxies interacting. These interactions can to some extent rejuvenate the galaxies involved by prompting star formation from the remaining interstellar gas. In this simulation, produced at the Pittsburgh Supercomputing Center, some very realistic galactic shapes are generated. Compare the result of this simulation with a photograph of the antenna galaxy pair which is in the constellation called Corvus. The resulting shape depends on just how glancing the encounter is, and the appearance to us depends on what angle of view we have. As the view rotates, we can see just how thin the galaxies really are. This simulation of a galaxy is realistic enough to have a hint of spiral arms caused by density waves. At the lower left of the screen, you can see a much smaller galaxy. Let's fire it in and see what happens. A galaxy is only just held together by gravity, and even this small intruder destroys its delicate structure.